Welcome to my video on absolute convergence. In a previous video, we took a look at the alternating series test. The alternating series test tells us if an alternating series, that is a series that has some power of -1 in it, as an example, whether it converges or diverges, because the terms in an alternating series go positive, negative, on, or negative, positive. So what we want to do now is determine what is called absolute convergence. And to do that, we need to look at the absolute value of a sub n. So if we have a series a sub n, and it is an alternating series. If it is an alternating series, then what we want to do is if the absolute value of a sub n, in other words, what we're doing with the absolute value is we're getting rid of the negative part. We're eliminating the negative. We're essentially making every term positive, because when you take the absolute value of something, you eliminate any negatives. So every term that would have a -1 multiplied to it will now have a +1 multiplied to it, and so every term is positive. That's essentially what we're doing here. If the absolute value of a sub n converges, then we say that the series converges absolutely. Then the series a sub n converges absolutely. What this means is that the series will converge whether the terms are alternating positive and negative or not. If all the terms are positive, it converges. If the terms are alternating, it converges. That's what it means to converge absolutely. Doesn't matter if you have alternating series or non-alternating series terms, it's still going to converge. All right, on the other hand, if the absolute value of a sub n diverges, that means that when all of the terms are positive, the series diverges. However, by the alternating series test, and if this end, a sub n, converges, so in other words, when we take the absolute value, it diverges, but when the series itself, as an alternating series, converges by the alternating series test, then we say that this will converge conditionally. Converges conditionally. What that means is that when the terms are all positive, it diverges. But when the terms alternate, positive, negative, it converges. A good example of that is the harmonic, 1 over x. 1 over x is a diverging series. But when it is an alternating series, it converges. Interesting. And finally, we have a third situation. If the absolute value of a sub n diverges, and by the alternating series test, a sub n diverges, then I guess you can probably figure out what happens. This series diverges. So those are the three different possibilities. We have converges absolutely, converges conditionally, or diverges. What I like to do is I'm going to draw you a little chart here now. This is something that I just thought up. And I think it will be helpful to remember what you have to do here. So we are going to have absolute convergence, conditional convergence, and divergence. And we have the absolute value of a sub n and a sub n. So the way that I use this little chart is if the absolute value of a sub n converges, it converges absolutely. Now, when that happens, we really don't need to do the alternating series test, because when this converges, it converges absolutely. This will automatically converge. So I leave it blank because I don't really need to do it, but this would converge. However, if the absolute value diverges, then we need to go on and do the alternating series test. And if it converges, we have conditional convergence. Finally, if they both diverge, we have divergence. All right, so that's a little chart that I like to use and that I share with my students to kind of remember what is going on here. And again, if you want to put a C in here, you can put a C in there, but you don't really need to. All right, let's do a few examples. The first example will be cosine of n pi over n squared. Now, this is an alternating series, even though it doesn't have a -1 in it, because we know that the cosine of n pi is going to fluctuate back and forth between 1 and -1. As an example, the first few terms of this series, when n is equal to 1, the cosine of pi is -1, and 1 squared would be 1. The next term, when n is 2, the cosine of 2 pi is going to be +1 over 2 squared is 4. The next term is going to be 3. The cosine of 3 pi is -1 over 3 squared, 9, etc., etc. You can see that the terms are going to be alternating because we're going from pi to 2 pi to 3 pi to 4 pi. So if you think of it as the unit circle, we're going from here to here to here to here to here to here. And so we're fluctuating between 1 and -1. All right, so this is an alternating series. So let's test for convergence. To test for convergence, we want to find the absolute value of this function. The absolute value of the cosine of n pi over n squared is simply going to be 1 over n squared. So what we do when we take the absolute value is we essentially remove the part of the series that is causing the alternating part. Okay, it's causing it to alternate. Well, what's causing it to alternate is the cosine function. So all I did was to find the absolute, to find a series or a sequence here that would represent this. I just removed the part of the a sub n that is causing it to alternate. So I end up with this. Well, this is actually fairly easy to determine whether it converges or diverges, because 1 over n squared is a p-series. A p-series, you will remember, is of the form 1 over n to the p. And when p is greater than 1, we have a series that converges. When p is less than or equal to 1, it diverges. And so p here is 2. That means that the absolute value of this series converges, which means it converges conditionally. If you go back to that little chart, we just did the first part. Now, do I need to go and test for the alternating series test? No. You could do the alternating series test. In fact, let's do it just for the heck of it, but it will automatically converge. Good review of the alternating series test. So the alternating series test, what we want to do is we're going to test 1 over n squared. So we want to find the limit of n approaches infinity of 1 over n squared. Well, that's 0. Check. Remember, that's one of the conditions that we have to have for the alternating series test. The other one is that each term, that n squared has to be greater than or equal to n plus 1 squared. Oh, and that's down in the denominator. Let me rewrite that. 1 over n squared has to be greater than or equal to 1 over n plus 1 squared. And a lot of times I will cross multiply these to show it, but another easy way to do it is this is always going to be true, because this denominator has the plus 1 in it. This denominator will always be bigger than this denominator. And if the denominator of a fraction is always bigger, but the numerator is the same, then this whole fraction will always be smaller. So therefore, we can see that 1 over n squared is greater than or equal to 1 over n plus 1 squared. So check. Both conditions of the alternating series test are affirmed, and so therefore it converges. So we already knew that by the absolute convergence. All right, example number 2. In example number 2, we have negative 1 to the n plus 1 divided by the 8th root of n to the 7th plus 1. All right, so to test for absolute convergence, the first thing that we need to do is to get rid of the alternating part. So the absolute value of negative 1 to the n plus 1 over the 8th root of n to the 7th plus 1 is simply going to be 1 over the 8th root of n to the 7th plus 1. So this is my a sub n. So I want to test this to see if that converges or not. So to test that, I think what I'm going to do is I am going to attempt to use the limit comparison test. The limit comparison test. To use the limit comparison test, I need to come up with a b sub n, a comparison series. So the way to do that, in my video on limits, and one of the things that you need to be thinking about for these things is the most powerful term. I always emphasize that. So if we look in the denominator, we only have one power, one term that has an n in it. So as n gets infinitely large, as the terms go on and on and on, this one here becomes insignificant. Because as n gets infinitely large, we're raising it to the 7th power, we're taking the 8th root, we're adding 1 to it, but that adding 1, it's like infinity plus 1 is still infinity. So this 1 becomes essentially unimportant. So I imagine what this would look like without the 1. And the way what it would look like is this. It would look like 1 over the 8th root of n to the 7th, which could be rewritten as n to the 7/8. Recognize that as a diverging p-series. This is a diverging p-series. All right, so it's a diverging p-series, and that's fine when we're doing a limit comparison test. So we are going to use that. I'm going to use it in this form, I think. So let's do that. In the limit comparison test, we want to find the limit as n approaches infinity of a sub n over b sub n. Remember. And so that's going to be the limit as n approaches infinity of, and I'm going to go from division to multiplication by the reciprocal just to save some board space. So that's going to be 1 over the 8th root of n to the 7th plus 1 times the reciprocal, which would be n to the 7th 8th over 1. Okay, and so now when we multiply these together, we essentially get 8th root of n to the 7th over the 8th root of n to the 7th plus 1. Well, what we can do is we can rewrite all of this because the index is the same. We can rewrite that all as just one big radical. So we could write the limit as n approaches infinity of the 8th root of n to the 7th over n to the 7th plus 1. All right, now what I'm going to do is what we've done many times before, is find the highest power of n and divide everything through by that. Okay? And so what I'm doing underneath here is I want to multiply inside the radical. So what I really need to do is I'm going to be multiplying by 1 over, not just n to the 7th, but n to the 7th, the 8th root of it, because I got to put it underneath the radical sign. And 1 over the nth root of n to the 7th. So what that's going to look like is the limit as n approaches infinity of the 8th root of n to the 7th over n to the 7th, n to the 7th over n to the 7th, plus 1 over n to the 7th. Okay, that's in order to put these n to the 7ths underneath the 8th root, I needed to do it as an 8th root. All right, well, underneath there, we end up with 1. This is a 1, and that would be a 1 over infinity. So we have the 8th root of 1 plus 1, 1 over n to the 7th. All right, I need a little bit of room here. So what we have is the limit as n approaches infinity of the 8th root of 1 plus 1 over, divided by 1 plus 1 over n to the 7th. As we let n approach infinity now, we can see what's going to happen. This is going to become 0. 1 over infinity will be 0. So we have 1 plus 1 divided by 1 plus 0 is 1 divided by 1, or 1. The 8th root of 1 is 1. Boom. So the limit is equal to 1. So remember what the, what are we doing? We're doing the limit comparison test says. The limit comparison test says if the limit of a sub n divided by b sub n is equal to some value L, then both series converge or both series diverge. Well, we already know that our comparison series, remember b sub n, which was 1 over the nth root, which is the same thing as n to the 7/8, is a diverging p-series. So since the comparison series is a diverging p-series, and the limit is equal to 1, which is L, then our series diverges. It does not have absolute convergence. So by doing the absolute value of a sub n, we find out that it diverges. The question now is, does it have conditional convergence? So looking back at that little chart that I made you, the first column is now a D. We need to go to the second column to see by the alternating series test if it converges or diverges. So with the alternating series test, remember we just look at the non-alternating series part of it, which is essentially what we're doing here now. And so we find out, does the limit as n approaches infinity of 1 over the 8th root of n to the 7 plus 1, what is that limit? Well, again, I showed you how to do these intuitively so we don't have to go through a lot of algebra. You can do the algebra, but I like to do this intuitively. As n is getting infinitely large, infinity plus 1 is infinity. The 8th root of infinity is infinity. 1 divided by infinity is 0. So check. Passes that part of the alternating series test for convergence. The second thing is we need to show that 1 over the 8th root of n to the 7th plus 1 is always going to be greater than 1 over the 8th root of n plus 1 to the 7th plus 1. Well, again, this denominator is always going to be a little bit bigger than this denominator. Just a little bit, by 1, but still, since this denominator will always be bigger than this denominator, this fraction will always be smaller than this fraction, and therefore check, passes. So by the alternating series test, it converges. So by absolute convergence, no, it diverges. Alternating series test, it converges. So therefore we have conditional convergence, which means that this series only converges when the terms are alternating. If all the terms were positive, it would diverge. And let's do one more example. So far, this is the longest video I've made. Really need to go for a coffee break. All right, this last one, the series from n to infinity of -1 to the n cubed over n cubed plus 1. All right, that is my series. So the first thing that we want to do is we want to find the absolute value of -1 to the n cubed over n cubed plus 1, which is simply going to be n cubed over n cubed plus 1. By the way, when you're doing your work, I like to see all your work. You may not show exactly as many steps as I do, but you really should show this. Some people will just skip this. That's what you're thinking. I'm just showing you what I'm thinking, but you really should show exactly what your series is. All right, so what we need to do is we need to determine if that converges. All right, so by that, I'm going to try the divergence test. Okay, remember with the divergence test, if the limit of the sequence does not equal 0, it diverges. So let's take the limit as n approaches infinity of n cubed over n cubed plus 1. All right, well, to do this limit, let's divide everything through by n cubed. So we're going to have n cubed over n cubed over n cubed plus 1 over n cubed, which becomes 1 over 1 plus 1 over n cubed. So we have the limit as n approaches infinity of 1 over 1 plus 1 over n cubed. And so as n gets infinitely large, this becomes 0, so we end up with a limit of 1. Okay, so by the divergence test, if the limit does not equal 0, it diverges. It does not equal 0. It diverges. So it diverges when we're testing for absolute convergence. So again, if the terms are all positive, this diverges. What we then need to do is look at the alternating series test and see if it converges or diverges there. So it does not have absolute convergence. And by the alternating series test, again, when we do the limit as n approaches infinity of n cubed over n cubed plus 1, we're doing the exact same thing, all right? We're doing the exact same thing that we just did. And so we know that this limit is going to be equal to 1. Now, by the alternating series test, this has to be 0 to converge. So the divergence test, alternating series test, you may get a little bit confused. The divergence test says if the limit of this does not equal 0, then it diverges. It's 1, it diverges. The alternating series test says in order for it to converge as an alternating series, then this needs to be equal to 0. Otherwise, it diverges. So it diverges by the alternating series test, and it diverges when testing for absolute convergence. So therefore, this simply diverges. So we've had one of three cases. We've had the case, so we have absolute convergence, conditional convergence, and divergence, where we did the absolute value of a sub n and a sub n. So this converged in the first one. This diverged, but that converged to give me conditional convergence. And now both diverge, which means this sucker diverges. All right, so I hope this is helpful. My lecture notes videos are available with different problems where I go over them. Some people like to just see someone explain this on the board as though they were sitting in class, so that's why I'm making these videos. Hope this was helpful, and I will see you guys in class.